All right. Good morning, everyone. I think we should get started. So, just the final reminder for homework number 5 that is due on tomorrow. Okay, so it's due on tomorrow by midnight. Um, so if you have any questions, I actually have office hour today in the afternoon. So let me know if you want to talk about any of the problems or tomorrow morning early at 9 o'clock to 10 o'clock. Okay. Um, and then don't forget there's SI section on Tuesday. If you want to attend it, you can sign it up. All right. So today we are going to check chapter 21 on circuits mainly. All right. So we'll get started here. So the first thing I want to talk about in this chapter actually is section 2 of this chapter. So it's on the electromotive force, or called terminal voltage. So this is referring to the voltage that a battery can supply. All right, so it's given a specific name called electromotive force, but keep in mind this refers to the voltage of a battery. Okay, it's similar to so electric potential provided by a battery is similar to the gravitational potential. All right, that you can build up by bringing an object to a higher altitude. So for example, here, if you put water on the top here, the gravitational potential it's built up, and then the gravitational potential energy is converted into kinetic energy. All right. So similarly here, if you have a battery from the two terminals, the positive terminal will have higher electric potential than the lower terminal of the battery. So then if you have this connect to a electric element, for example, a light bulb here as a resistor, then the current will flow from the positive terminal through this element towards the lower terminal. Just like water, it's going to flow from the higher position to lower position. So because there's gravitational potential there. Similarly here for battery, the terminals, two terminals, you have actually electric potential across. Okay. All right. So the electric potential across the terminals of battery is called EMF, or electromotive force. Okay, so in symbol it's EMF, the abbreviation for electromotive force. Okay, it's given a sign epsilon specifically to it, but it's just the voltage. Okay, so just keep in mind this is voltage here. So then the amount of work it takes for a charge delta Q to move from one terminal to the other will be equal to the charge times the voltage, right? The voltage is the epsilon here. So work equal to delta Q times epsilon, okay? Or you can say it's delta Q times V. V is the same as the, epsilon is the same as V. All right. Now for ideal battery, we are usually ignoring its internal resistance. So for the battery inside itself, there's electrode which carries small resistance. So in reality, there's small resistance in the battery. So then when this is connected to a electrical element, for example, a resistor, then this small resistance is in series with the outside resistor, okay? So then in that sense, the voltage that the battery is supplying actually will be divided into two parts. One part is it's applied to the internal resistance of the battery, and then the rest to the outside of the circuit elements in the circuit. So then the power supply to the circuit actually is going to be small than the EMF. Okay. So for the lab you guys did last week, you probably realized that your battery voltage is higher than when you close the switch, right? If you measure the voltage of the battery directly, it's higher, but once you close the battery and then if you try it, you'll find that the battery is lower. So it's because of this internal resistance, okay? So then the voltage can be supplied by a battery is slightly less than its specific potential that can provide. Okay. All right. So the load, the current in the load, you can calculate by using this equation. So if this is epsilon, now this is capitalized word epsilon, it should be divided by a resistance, the load resistance, the outside, okay? So the circuit resistance of the circuit itself, plus the internal resistance of the battery. That gives you the overall current in the circuit, okay? So that's in theory. Most of the time, this guy is a very small, R is very small. So if not specifically mentioned, and we are going to ignore this R, all right, when you are looking at the problem. But just keep in mind, there might be a scenario that you have to consider this small R, okay? If the circuit itself has very small resistance, then you want to consider that resistance of the battery itself. All right. There are different types of batteries. For one of the very old-fashioned battery, you will actually have like sulfuric acid, okay, as the electrolyte solution, and then you have two electrodes, okay. So the these days, like the gasoline cars, the battery of the gasoline cars, actually like the 12 volts batteries, it's actually kind of like this. All right, you have two electrodes and then have some electrolyte solution there that provides with you the power, the voltage. Okay, so there are chemical reactions involved there. So you can find more details in the electrochemistry section of your um, chemistry class, okay? But that's the typical of what you would have. All right, so that's the section on the battery. Any questions you guys might have on batteries before we move on? All right, so if not, then we'll jump back to the first section of this chapter. We will be looking at resistors and then the combination of resistors. Okay, so for resistors, you can have them in combination in series or in parallel. Okay, so just similar to capacitors, they can be in series and in parallel. And then what's more, they can be in complex combination of like some parts of the circuit are in series, some parts are in parallel, and then mixture of each other together sometimes. Okay. So for the elements to be in series, they share currents. Okay, so that means they have the same current going through. So for example, in the figure A here, you have 4 resistors, they are in series. So the current going through R1, resistor 1 will be the same as the current going through resistor 2 and 3 and 4, etc. Okay, now in configuration B, in the figure B here, so if you have the resistors in this combination, then they will share the same voltage. So that means they are in parallel to each other. So the voltage across R1 will be similar to be the same as the voltage across R2, R3, R4. They do not necessarily share the same current because if the R's are different, then according to Ohm's law, I is equal to V over R. So V will be the same, then I will be different across each of them. Okay. So to determine if the resistors are in series or in parallel, these are the rules. And you want to see if they share the same current, means the same current going through each of them, or they share the same voltage. That means the same voltage apply across each of them. So if they share the current, that means they are in series. Otherwise, if they are sharing voltage, that means they are in parallel to each other. Okay. All right. Now let's take a look. If you have several resistors are in series, so in this case, R1, R2, and R3, they are in series, connecting them one after another. And then if this combination is powered by a battery over here, all right, so then you will see actually this can be equivalent to the combination of the resistors can be represented by a single equivalent resistor. Okay, so in that case, So let's see what's the relationship between the resistance of each of these ones and then the resistance of the equivalent resistor here. So because they have the same current going through, all right, so you can, so let me show you the algebra here involved, all right. So they share the same current, so that means voltage across each of the resistors V1 plus V2 plus V3, okay? That should be equal to the voltage that the battery can supply, all right? And then this one, V1, according to Ohm law, should be I times R1 plus, for V2 should be I times R2 plus V3 should be I times R3, okay? That equals to V, all right? So I is the same because they are in series, so you can single out I times R1 plus R2 plus R3 equals to V, okay? Now, on figure B here, so the I will be this I again, all right, times this R equivalent, that should be equal to the voltage of the battery, okay? So you can see V is equal to this guy, V is equal to that guy. So I times R1 plus R2 plus R3 is equal to I times R of the equivalent resistance, right? So I and I will cancel out. So that tells you for equivalent resistance, the so let me put this way, you can see that better. All right. So then you can see equivalent resistance should be equal to the summation of the resistance of each of the resistors are in series. Okay. So that's when you have resistors in series. Now take a note here, when we have capacitors in series, that's the opposite, right? For capacitor in series, you take inverse of the capacitance of each capacitor and then add them up and then take an inverse again to get the equivalent resistance. Okay, so in this case, just remember for resistors and capacitors, they are opposite to each other, the other way around. Okay, all right. So let's go back here. So when you have resistors in series, you add them up, the resistance up of each resistor to get the equivalent resistor. Okay. And that's not the same as, that's actually the same for similar to capacitors in parallel to each other, okay, but the other way around. Next, let's take a look on when you have resistors in parallel to each other, okay, so you have R1, R2, and R3, they are connected. So the blue lines here just indicates how the currents are flowing, okay, but for the circuit itself, look at the black lines and then the elements that those lines are connected to. So R1, R2, and R3, they are parallel to each other, so they are powered by the same battery over here. So that means the voltage across each of resistors will be the same. All right, so in that sense. And then similarly, you can represent the combination of the three resistors by a single equivalent resistor like this. Okay, so let's see how that turns out. So the conclusion is over here, but let's take a look on the algebra here, how to derive this. Okay, so you will see that for each of this one, so you're going to see the current, when the current going out of the battery, will split it actually into three branches, okay? And then each one is like I1 on R1, I2 on R2, I3 on R3. So each of these current combined, I1 plus I2 plus I3, that should be equal to the overall current going through the battery, right? So you can write that, again, let me just stop sharing screen. You can pull this PowerPoint on your side along with this. But basically, for the total current is equal to I1 plus I2 plus I3 this time, okay? Now for I1 is equal to V over R1. For I2 is equal to V over R2. For I3 is V over R3 according to Ohm's law, right? They share the same V, okay? Now, if you replace the combination of the resistors in parallel with an equivalent resistor, then the current going through that resistor will be V over R EQ, okay, equivalent resistance. This is the voltage from the battery, okay? So you can replace this guy, the voltage from the battery, with this. So you can say V over REQ is equal to this, okay? So then you see that because V is the same across here, the turns, so you can cancel the V out, okay? So then 1 over REQ is equal to 1 over R1 plus 1 over R2 plus 1 over R3, all right? So that's the relationship when you have 3 resistors are in series, are in parallel in this time to each other. Now, if you have more, then you just add the inverse of each one up, okay? Resistance, inverse of resistance up for each of them. All right. Sorry, I'm sharing this screen here. Okay. So then for equivalent resistance for the resistors in parallel, inverse of the equivalent resistance is equal to inverse of each of the resistors adding up, okay? Now again, this gives you inverse. So if you want to calculate this guy, you want to do inverse of the sum of all this 1 over R, okay? It doesn't give you the resistance itself, okay? It's just inverse of the resistance. All right, so resistors in parallel is similar to capacitors in series then, okay, in that sense. Okay. So now let's take a look on one example here involving resistors. So this one says A, given a 48.0 volt battery and a 24.0 ohm and another 96.0 ohm resistors. Find the equivalent resistance and power of the circuits when the resistors are in series. And then B, repeat part A for the resistors are in parallel, okay? So you guys can give it a try. And then we can take a look at the solutions in a few minutes together, okay? But basically you have first one as they are in series. So that means there's a battery over here which supplies 48 volts. Now the two resistors, you can see one here, and then you can see one there, down there. They are in series, okay? So R1, R2, and then V or epsilon if you want to use epsilon. Epsilon is 48.0 volts, R1 is 24 ohms, and then R2 is 96 ohms, okay? In B, you'll have them connect in this fashion that they are parallel to each other. So you might have a switch in the circuit, okay, something like that. And then, so this is R1, this is R2, this is your battery, okay? So you're looking for R equivalent for each of these parts, and then also the power of the circuit itself, okay? So for power, you can do either way. You can do epsilon times I, V times I, okay? There's several formulas. So V times I or V squared over R or I squared times R, okay? Just remember, those are the equations you might use. All right, so give it a try, and then we can take a look at the solution together in a few minutes, okay? All right, so let's take a look at the solution together here. So in part A, the two resistors are in series with each other. So then for the overall resistance or the equivalent resistance, you actually have them combined. Okay, so R1 plus R2 in this case. So these two are in series. So you will have 24 plus 96 ohms. Okay, that gives you 120 ohms. All right, that's the equivalent resistance for the two are in series. Now for the power, you are given the voltage, okay, from the battery as 48. You know R, the equivalent resistance. So then you put the pick this guy, all right, easier for you. So it's V squared over R, this case. V is the 48 volts. Remember to square it divided by 120 ohms, okay? That will give you 19.2 watts as the power of this circuit, okay? Now on part B here, these two, the two resistors are in series, in parallel. So this time, the equivalent resistance, 1 over equivalent should be equal to 1 over R1 plus 1 over R2, okay? That's the equation to use. Now to calculate this, you want to do inverse of the 1 over R1 plus 1 over R2, okay? So you can plug in the numbers there, 1 over 24 plus 1 over 96 ohms, and then inverse of it, okay? That will give you 19.2 ohms as the equivalent resistance of the circuit. All right, and then for power, again, you will be using this V squared over R, in this case, REQ. Okay, so this is again REQ over there, the same here, REQ, because you're looking for the power of the circuit, of the combination of the two. All right, so it will be 48 volts again, squared, divided by 19.2 ohms. Sorry, ohms here. That will give you 120 watts. Okay. All right. Any questions you guys might have? All right. So if you are clear, so I just want to make a note, like for the everything we use in our household, each of say the light bulbs or the appliance, they are actually in parallel to each other. Okay. So in that case, if one of them will be burned. So for example, if this is burned, then you still get the voltage across this guy as 48 volts. Okay. So in our household, it's 120 volts. Okay. So everything in our household is they are in parallel to each other. Okay. Just keep that in mind. All right. So we just look at the resistors are in series and in parallel, okay, individually. But in many cases, when you have a circuit, for example, especially when inside the electronics, for example, in your laptop or in your calculator, in the multimeter, etc. So a lot of times you have resistors are in more complicated combinations. For example, you might get a combination like this. Okay, so this guy is in series with the rest, but inside part of the circuit, you have some that are in parallel to each other, and then you might be having another part in parallel to each other. Okay, and then the combination of the two in parallels are in series to each other actually after that. And then in addition to that, they are in parallel to this guy. Okay, so things might get very complicated. But how do we deal with when you have circuit that have a lot of resistors? They are in combination of both, like in series and in parallel. Okay, so the rule is to just look at the parts of the circuit that are either purely in series and in parallel first, and replace that part with just an equivalent resistor. All right, and then starting from that, you'll be doing this again. So for example, in this one, you might be able to identify that those three are in parallel to each other. So you can replace those three with an equivalent resistor called RP here. Okay, so these three are replaced by RP. And then these two are in parallel again. They can be replaced by a RP prime. Okay, so then the complicated circuit becomes a little bit less complicated one. Okay, still here you have complicated ones because these two are in series, but they are in parallel with this guy. Okay, so then you'll be checking on this now less complicated circuit and identify which part of it is purely either in parallel or in series. Okay, so you can you might identify these two are purely in series. Okay, and then replace those two with a R equivalent. We call RS here. So then that's replaced by RS. Okay, so this is replaced by just one single one. So that means two resistors becomes one here. And then now it became this one, this circuit, right? So then take a look on this circuit. Now those three are not purely in series or in parallel. So you want to check again, you identify that these two are purely in parallel to each other. Okay, so then the circuit reduced to this guy, replacing those two in parallel with this guy, RP prime, double prime. Then you have now circuit reduced to this one, rather simple one. These two are purely in series to each other. They can be replaced by a single resistor. Okay, so you can calculate each of those equivalent resistors, like equivalent of those three, and then equivalent of those two, and then equivalent of these two, equivalent of these two, okay, etc. Now, the challenging part is how can you identify which part of the circuit you will have resistors just purely in series or in parallel, okay? Again, it takes practices, but the rule here is you can take a look on those parts, and then you can, if they are having the same current, then they are sharing, they are in series to each other. Okay, so if they are in parallel, that means they are sharing voltage. Okay, so for example, if you check on those three, you can see those three will have the same voltage across. Okay, because they are purely in parallel. Okay, now that might be easy to tell, but if you want to see if R1 and then this guy R7, if they are purely in series or not, right? Because they look like it's connected one up to another. But here you can see battery goes through R1 and then enter this point. The current going through R1 will be split into two. One goes through this one goes through that branch. Okay, so then that means current going through R1 and R7 are not the same. Okay, so those two are not in series, right? It looks like they are, but they are not, actually not. Okay, so that's how you can tell. All right. Let's take on a look on this example here. Okay, so this one says, consider the circuit showing here. Find an equivalent resistance of the circuit. So that means find the equivalent resistance of the whole circuit. Okay, and then B, the current through each of resistors. All right. So maybe you guys can focus on A first, okay, and then take a look on which ones are purely in series or in parallel first, and then reduce it to a less complicated circuit, and then go step by step. Okay, just consult the example in the previous figure, and then try to see how far you can go on this one. Okay, and then we can take a look on the solution together in a few maybe a couple of minutes. Okay. All right, so let's take a look on this one together now. So in part A, I'm looking for the equivalent resistance of the whole circuit, okay? So there are 4 resistors here. You want to focus on the parts that you only have resistors purely in series or in parallel, okay? So you can, there's one trick to do here. You can actually indicate the flow of the current in the circuit, okay? So flow of the current should go from the positive terminal starting from there, all right? And then you can see that I goes from here now through the wire. So the lines are the wire, and then it will enter into this two here, okay? These two um, junctions here, all right? These two branch. So you will see that one will go through here, one will go through there. Okay, so you can say this is a total I, the same I there. Now you can say this is might be your I1, your I2. So I split into two, I1 and I2. Now for I1, it goes through this guy. You can see that I1 will also go through this guy, right? And then goes back over here. This is I1. So I2 will go through here and then here. At this point, I1 and I2 will merge again and then becomes I, the overall I, going through this guy. Okay, so you can actually indicate what's the current going through each of the element to see if they are in series. Okay, so if you are doing this way, then it shows clearly that these two are sharing I1, right? So 6.2 ohms and 12 ohms, they have the same I1. So these two are in series, right? So these two are in series to each other. So you can replace that part with a RS, R in series. So then your circuit will become, all right, little bit simplified this time. So you'll have like 15 volts there, and then the current going through there, and then this is the 7.5, this is the 11. All right, now on this branch, the two just becomes one. Okay, so this is the R of S, that guy. Okay, so you can see now your circuit simplify as this one. Okay, now the same thing here, you can track to see if any of them will be in series. So you can say this is the current I goes here. So this will be I2 again, but this will be I1. They are different, right? And then they merge at this point becomes I again. So I here. So these two are not in series. Okay, so they are actually in parallel to each other because they are connected in this fashion. Okay, so you can see these two are in parallel. Okay, so you can replace that with a equivalent resistor of R in parallel, RP, okay? So this is the 7.5 ohm, this is the 11 ohm. Now you can calculate this RS, okay? You can calculate right now because they are in series, so then equivalent will be equal to 6.2 plus the 12. It becomes 18.2 ohms, okay? So this guy is the 18.2 ohms, okay? But now these two are in parallel. You identify that those two are in parallel. You can solve for R equivalent for those two in parallel. Okay, so it's 1 over 7.5 plus 1 over 18.2. Okay, inverse of that. Okay, so 1 over RP should be equal to 1 over 7.5 plus 1 over 18.2. So then RP will be equal to this one inverse. Okay, so you can calculate that. That will tell you it's this is 5.31 in ohms. Okay, so then now your circuit further simplify as just a battery connect to this whole thing is this RP. Okay, so RP and then with the 11 ohm. Okay, so it becomes that 11 ohm. Now you can see this is simple one. This is just these two are in series with each other. Okay, so your overall equivalent then will be equal to these two are in series. So 11 ohms plus this RP of 5.31 ohms. Okay, that will tell you this is going to be 16.31 ohms. Okay, or 16.3 ohms. So this is your equivalent resistance for the whole circuit. Okay, so again, first identify the part that's purely in series or in parallel, and then replace that with the equivalent resistor. Then simplify your circuit, okay, with the equivalent resistor, and then check on the circuit again to identify a part that is either in parallel or in series. Then replace that part with a equivalent resistor again, just repeating that, and then further simplify your circuit. Okay, so at the end you get this simple circuit like that. Okay, so that gives you the equivalent resistance of the circuit. Questions you guys might have on this part, on part A? All right. So if not, then we are going to check on part B. It says find the current through each resistor. Okay, so let's see that. So originally you have 4 resistors. Okay, so you are going to find, so as we indicate initially, total current is I. That is the current going through this 11 ohms. Okay, so I is for 11 ohm, and then I2 is for 7.5, I1 is for both 6.2 and 12 ohms, okay, in that sense. Okay, so you can calculate those three, I1 and I2. Okay, so that's what you are looking for. So let's see here. We are looking for I1 and the I2. Okay, and then we you might be already figured out that, so I should be equal to I1 plus I2, right? Because I goes in this point and then split into 2, I1 and I2. So I should be equal to I1 plus I2. Or on this point, you can see I1, I2 comes in as and then comes out as merge. They merge, it becomes I. So I is equal to I1 plus I2. Okay, so then really you are just looking for I and then either I1 or I2, or like either I1 and I2, you'll figure out I. Okay, so in that sense, we can take a look this most simple one here. Okay, so I goes through there, then comes back through this guy, right? So I there. So you actually can figure out what's the overall current through the whole circuit, which will be equal to this guy, right? So I overall then should be equal to the voltage, all right, supplied by the battery divided by Req, okay, the equivalent of the whole circuit, okay? So then that gives you 15 volts divided by 16.31 ohms. That would be your I, okay? Because it's the I going through this guy, it's the I going there, it's the I for the whole circuit. That should be the current going through the 11 ohms, okay? So this one then will give you 0.92 amps, okay? So this is for the 11 ohm resistor, okay? Now next, you just need to figure out either I1 or I2. Then you will have the other one, okay? So let's take a look on how we figure out I1 or I2, okay? So because you have this guy already figured out, that I figure out, so I think we have used this circuit, okay? So we can look back, we can take a look on this one here. So if I have this I already, I can figure out what's the voltage across this guy, okay? And then if I have voltage across this guy, then voltage on across this part of the circuit should be, you should be able to figure that out, right? Because voltage across here plus voltage across here should be equal to the voltage supplied by the battery, right? So that's how you can see, because this one is in series with that part, okay? Or you can look at this one. This voltage on this plus the voltage on this should be equal to the voltage from your battery, okay? Just similar there just replace this 2 with this equivalent. Then you can figure that out. Okay. So we have the overall voltage epsilon. We have the I here. We have this ohms. We can figure out what's voltage across that guy. Okay. So voltage across the 11 ohms. Let me just put it down as V sub 11 ohm. That should be equal to the I times the 11 ohms, right? The I on the 11 ohm times that. So 0.92 amps times my 11 ohms. That should give you the voltage across the 11 ohms. Okay. So that will give you, let me see. 10.12 volts. Okay. So if that's the case, then voltage across the 7.5 or across this part, okay, V of that parallel. So I'm going to call that V parallel. Okay, so voltage on this part, the VP, V sub P. Okay, VP then will be equal to the epsilon by the battery minus the voltage on the 11 ohm, right? So it'll be 15 volts minus 10.12 volts. Okay, so that will be 4.88 volts. Okay, so now I have voltage across this guy to be 4.88. It should be also this one over here. Okay, so voltage on this one is 4.88. Voltage on this one is also 4.88 because they are in parallel. Okay, equivalent to this guy. And the two in parallel is equivalent to this guy. So then we have voltage on this one to be the same on the voltage on that part. Okay, so then you can calculate your I2. I2 is the current going through the 7.5. I2 will be equal to the VP over the 7.5 ohms. Okay, so that will be 4.88 volts divided by 7.5 ohms. Okay, that will give you approximately 0.65 amps. Okay, so this is the current for 7.5 ohms. Okay, and so then the current for the I1, the current for 6.2 ohms and 12 ohm should be I1 should be equal to the overall current minus I1. Okay, so that would be I minus I2. Okay, so it will be 0.92 amps minus 0.65 amps. Okay, that should be about 0.27 amps. Okay, so that's for 6.2 ohms and for 12 ohms as well. Okay, because they are in series with each other. Okay. You can probably figure out the currents in another method. Okay, so there's multiple ways of doing that. Okay, so you don't have to be exactly as the way I did it. Okay. All right. You might be figuring out like the let's see, once you figure out this current on this guy should be the same as this guy, all right? Then instead of figuring out the current on this one, you can figure out the current, or instead of figuring out the voltage on this one, you can figure out the voltage on this guy directly by using the I, this I times the RP, which is 5.31, okay? And then that would be giving roughly 4.88 again, maybe 4.89 is maybe one decimal difference because of rounding error here involved, but should be the same. So then after that, you directly can calculate what's the voltage across. This guy will be the voltage across those two in parallel. Then you can figure out either I1 on this one or I2 on that one, okay? So either way. All right. Any questions you guys might have on this one? Okay, so if not, I think we are going to stop here for today, and then we'll be checking on the other sections next time. All right. So I'll see you guys in class again on Wednesday then. Okay. Bye guys. Have a good day.